Hello everyone and welcome to our channel, Mootechie. Today we're diving into the fascinating world of ethanol production, a process with significant importance in the food, fuel and pharmaceutical industries, particularly relevant for dairy technologists, where byproducts like whey can be utilized. The commercial production of ethanol became feasible on a large scale after the 1906 Industrial Alcohol Act. This act allowed for the sale of tax-free alcohol, provided it was first denatured to prevent its use in alcoholic beverages. Ethanol has a wide range of uses. It serves as an organic solvent in products like paints, perfumes, inks, varnishes, and soaps. Its most popular use is as a motor fuel and fuel additive, known as gasohol, valued for its renewable nature and environmental benefits. In homes, ethanol is a potent food preservative. It's also used in antiseptic soaps and cosmetics, due to its effectiveness against bacteria, fungi, and viruses. Of course, it is consumed around the world in beverages like beer, wine, and whiskey. Additionally, it plays a crucial role in pharmaceuticals, the preparation of essences and flavorings, as a fluid in thermometers, and for preserving biological specimens. The chemical process behind ethanol fermentation is a biological one, where yeast cells convert sugars into ethanol and carbon dioxide. The basic chemical reaction is, one molecule of glucose yields 2 molecules of ethanol and 2 molecules of carbon dioxide. This process begins with glycolysis, where glucose is broken down into pyruvate. Under anaerobic conditions, or even aerobic conditions for some yeasts like Saccharomyces cerevisiae, this pyruvate is then converted into ethanol. Not all yeasts are suitable for brewing. The choice of yeast depends on the raw material used. For instance, different strains are used for molasses, grains, or whey. A suitable fermentation strain must grow rapidly, tolerate high sugar concentrations, produce abundant alcohol, and be resistant to the high alcohol concentrations it creates. The media of feedstock for commercial production is diverse. It includes blackstrap molasses, which is most common, as well as corn, potatoes, grains, wood wastes, sulfite waste liquor, and whey from dairy processing. For molasses, it is diluted to a sugar concentration between 10 and 18%, as higher concentrations can harm the yeast. The pH is adjusted to between 4.8 and 5.0 using acids. For starchy materials like corn or barley, the starch must first be broken down into sugars using methods like malting, acid treatment, or enzymes from fungi like aspergillus. The fermentation itself takes place in large reactors. The temperature is maintained between 21 and 27 degrees Celsius, though cooling is often required because the process generates heat. Fermentation typically lasts for 2 to 3 days, resulting in a broth containing 6 to 9% alcohol by volume. This represents a very efficient 90 to 98% conversion of the sugar into alcohol. It's important not to confuse this yield with proof, which is a measure of alcohol strength. Proof is twice the percentage of alcohol by volume. Finally, we move to product recovery. Ethanol is separated from the fermentation broth using continuous stills. Through successive distillations, a concentration of 95% ethanol is achieved. To obtain 100% or absolute alcohol, a special technique is needed. This involves adding benzene to form an azeotropic mixture with the remaining water. Upon distillation, the benzene-water-ethanol mixture is removed first, followed by a benzene-ethanol mixture, leaving behind pure absolute ethanol. Thank you for joining this session on ethanol production. We've covered its history, vast applications, the biochemical process, suitable microorganisms, feedstock options, fermentation conditions, and the recovery process. This knowledge is key for understanding how agricultural and dairy waste streams can be converted into valuable products.